Okay, hello everybody. So today we're going to be talking about the supplemental material for approximate integration. So we already introduced some of these ideas in class. We're going to be looking at some of the background ideas in the supplemental material today, and then we'll be talking about Simpson's rule at the end, as well as the background material for it. We discussed Riemann sums already, and I think we're pretty comfortable with that. But moving on to the integration methods that are somewhat new to us. What are the ideas behind these? Why did we develop these methods the way that we did? And the basic idea behind the development of these methods is to create methods, create approximate integration methods that will be exact on certain classes of functions. And better methods in a sense are exact on broader classes of functions. So we kind of saw before, and I think it's kind of sensible to think that Riemann sums are exact on constant functions, because Riemann sums, the areas are boxes with flat tops, and constant functions are flat. So that area, that approximate area, so to speak, should be a perfect representation of the actual area. Now, one minor note, when I say a constant or linear function, generally I'm talking about piecewise constant or piecewise linear in this discussion. So we could always take an integral over a piecewise function, and we could break the region of integration into different regions based on those different pieces. So we could always break a piecewise constant into several different constant functions and integrate each of those individually, and so on for linear and quadratics and so on. So when I say, this is exact on linears, really, I mean, it's exact on piecewise linears. So we kind of intuitively, I think, understand that Riemann sums are exact on constant functions, but what about a linear function? Well, that's where the trapezoid rule comes in. Now, one more note that I want to make here is that instead of integral a to b, we don't want all of these a's and b's floating around. It just makes the algebra that much more complicated. We're going to use integral 0 to 1 f of x dx. And a simple substitution will allow you to take the interval from 0 to 1, convert it into an interval from a to b, and the techniques are going to work exactly the same. Whether it's exact on constants or linears, the analysis is all going to work exactly on this, exactly the same. So we're going to work with the integral from 0 to 1, and we often use the abbreviation log without loss of generality. So anything that we can say regarding these numerical methods over the interval 0 to 1, we'll be able to say over an interval a to b. It's just that this simplifies our algebra. Okay, so let's look at the trapezoid rule. The goal of the trapezoid rule is to create a rule, an approximate integration method that is exact on linears. So what's my idea here? I have on 0 to 1, I have a linear function, f of x, and let's call it mx plus b. So I have an actual area under the curve, and I could have an approximate area under the curve. I have heights over here, f of 0 and f of 1. So I'm presuming I can evaluate the function at 0 and 1. And what I am interested in is what's the integral 0 to 1 f of x dx, which is the integral 0 to 1 mx plus b dx. Okay, so we want to, on one hand, have our approximate integration method be exact for this integral, and we can actually compute exactly what this integral is. And you might say, well, why isn't this kind of a dumb thing to do? We know what the exact solution of this integral is. Why are we going to construct an approximate integration method based on that? Well, we'll see kind of at the end of Calc 2 that very complicated functions, like say sine of x or say like e to the x, can be better and better approximated by constant linear, quadratic, cubic, and so on functions. So when we get to the discussion of power series and Taylor series, we'll see that kind of the more terms that we add on to our polynomial approximation, the better approximation we get to the actual function. So if we're trying to integrate a very complicated function, let's say like sine of x squared or something on 0 to 1, we can think of that as kind of having a linear part plus some other nonlinear stuff. Or we could think of it as having kind of a quadratic part plus some other higher order stuff. And the more that we can kind of encapsulate under that exact the exact approximation, if you will, the better our approximation method is likely to be, the more accurate it's likely to be. So we're going to proceed with this. We want to integrate mx plus b from 0 to 1. So we get, this is going to be x squared over 2. So we get m over 2 evaluated at 1. And evaluated at 0, we get no contribution. And then plus b, right? bx evaluated from 0 to 1. And we want to take f of 0 and f of 1, just those points that I can just evaluate the function at those points. And I want to have weights, let's call it weight 0, w0, and weight 1, w1. So what I want is I want to create an approximate integration method where I have, just like up here, where I have weights multiplied against function evaluations. Even if I have a complicated function, I should be able to evaluate it. Something like sine of x squared, I can plug in 0, I can plug in 1, I can get the evaluation. I want to take those evaluations, multiply them by weights, add them together. That's a straightforward process. And again, I'm trying to construct this in such a way that it's exact on linears. So I want these two to be equal to one another. Or in other words, this is w0, f of 0 is just b, plus w1, and f of 1 is m plus b. So my goal is to find w0 and w1 such that these two are equal to one another. Okay, so how can I do that? Well, I see that what's my coefficient of m? w1. I see that w1 m has to equal 1/2 m. So w1 has to be 1/2. And then I have w1b plus w0b, or 1/2 b plus w0b has to equal 1b. So w0 also has to be 1/2. So that's a pretty easy, right, algebraic step to do. And I could see that I can approximate the integral 0 to 1 f of x dx as 1/2 f of 0 plus 1/2 f of 1. Or we could say that this is 1/2 f of 0 plus f of 1. Now to generalize this, right, I could generalize this to more general functions and I'd lose that exactness, right? If I had a general f of x, then this exact would become an approximate if f of x was no longer constrained to be a linear. So this is where my approximate integration comes in. And I suppose this equality is actually equal, and this one is the approximate. Again, I could generalize this to an integral from a to b. And I could generalize this to a situation where I have, I have x0, x1, x2, x3, x4, where I have n subintervals. I just treat each subinterval just like one of these, these intervals like the integral a to b, it would just be integral 0 to 1/4 or something. Each one of these subintervals would work the same way, and I would just kind of chain them all together. But I think we see the fundamental structure here. From 0 to 1, my delta x in this case was 1 minus 0 over 1, or just 1. So I see my delta x over 2 times f naught plus f1. And that's what I see here, here, and here. And where would I get these factors of 2 coming from? Well, that would be if I had some internal points of evaluation. This would be, say, the right-hand side of one of the trapezoids, but the left-hand side of the next trapezoid. So I would get 2 contributions of, say, f of x2 or f of x3, f of x1 in this this red example over here. So if we start off with this kind of basic method, integrating 0 to 1, and just using one subinterval or just one interval, that can easily generalize to the fully general case up here. We're not going to go through the error analysis. That would be something that maybe we could talk a little more about, say at the end of the class, whenever we have a little more information on Taylor series and how they work. But for now, we're just going to kind of take that for granted. But note that the error analysis, this k term here, is kind of consistent with what we just discovered. That if we can bound the second derivative above by some number, then the error is going to be bounded above by something related to that number. Or in other words, if the second derivative is 0 everywhere, as it would be on a constant function, then the error is bounded above by 0, so the error is, of course, 0. Okay, so something that we might be thinking about now is, okay, well, we have this midpoint rule. But I told you that the midpoint rule actually has this similar behavior to the trapezoid rule, right? Where does that come from? Well, let's kind of revisit Riemann sums and then take a look at the midpoint rule, where that might come from. So again, I have integral 0 to 1. I have a linear, so not constant, just straight line. I have f of 0. I have f of 1. And again, I want to create an approximate integration method that is exact on linears. But here, what it seems like I'm doing, it seems like I'm cheating somehow, right? Because I want this to be just some weight times f of something. It seems like I'm cheating because it seems like I have 2 terms that I need to address, but I'm trying to do that. I'm trying to address both terms with a single weight and a single function evaluation. How is this working? Well, let's take an aside really quick and let's look at a constant function. So we'll kind of revisit Riemann sums. I have a constant function. F of x equals c. All right, so what do I have here? I need to, in this case, integrate 0 to 1 of c dx. And I want it to be, well, what do I want it to be? I want it to be some weight times f of something. This seems like it's pretty reasonable, right? It seems like it's pretty reasonable to say that if I have one constraint that I need to meet, I can meet that with 1 degree of freedom. What is integral 0 to 1 c dx? That's just c. That's weight times, well, f of, it doesn't really matter if we pick f of 0 or f of 1 or f of 1/2, or we can pick really any f of, I'll use a variable here, c. So the variable that often comes up in these kind of Taylor series kind of things. A lot of times we use the Greek letter xi, xi for this. It looks kind of like an E with a couple of tails on it. All right, so we note that it actually doesn't matter where I evaluate the function because it's constant. So C equals WC says that W has to be 1. And I could choose to evaluate the function at 0 or at 1 or at a half or at, any number between 0 and 1. So my approximate integration method would really be just integral 0 to 1 of C dx is f of C for any C in 0, 1. All right, so what if I did the same thing up here? I note that something interesting occurred here. That there might be something deeper that you've noticed here is that I put in a degree of freedom where I can choose to evaluate my function. And it actually didn't matter to get exactness for the constant function. I put in an extra degree of freedom. I could choose where to evaluate my function anywhere between 0 and 1. And it turned out that it didn't matter. That might be suggestive of the fact that I still have some wiggle room. I still have a degree of freedom left implicitly somehow. Somehow there's like a symmetry or something here that's making things work out a little nicer than I might expect. Okay, so let's come back up here. That might be our kind of very rough intuitive rationale for thinking that something like this might work. So again, what was integral 0 to 1 mx plus b? Well, from up here, we did that already. We saw that was m over 2 plus b. And what's f of c? It's m c plus b. Now, one thing that I notice is that I have a b here, I have a b here, so b equals wb. That tells me that w, my weight, has to be 1. So that's fixed by matching up the b terms. But I also can choose where to evaluate. I don't have to evaluate my function just at 0 and 1 or one of the two. I could actually choose to evaluate my function at a different point, C. And I could use that freedom that I could decide where to evaluate my function. I'm still only doing one function evaluation. It's still only that much cost for me, but I have some freedom here. I can use that freedom to match up my m terms. So matching up the b terms fixed what w had to be, my weight, fixing the setting the m terms equal to one another fixes my c as 1/2. So what do I have? I have the integral 0 to 1 f of x dx for the linear function. This will be exact if I do 1 f of 1/2. Or in other words, if I choose to evaluate at the midpoint of my interval, what geometrically is going on here is I can basically think of this integral, this area under the curve, as if it was the area under a constant function, because this bit here perfectly flips over and fills in that triangular section that's missing. So I have some really nice symmetry here that I can leverage. So the midpoint rule, I can actually get away with doing one function evaluation instead of 2. Where was it up here? Instead of 2. And I can get the same behavior. I can get the same exactness on linears with the midpoint rule as with the trapezoid rule. Now, there are some other nuances for these different rules, and that would be maybe something that a course in, say, numerical analysis would dig into to great depth. But at least from this perspective, the midpoint and the trapezoid rule kind of have similar performance. But the midpoint rule only has to have one function evaluation, where the trapezoid rule has to have 2. So that seems to take a performance hit. There's one detail to notice though. The midpoint rule, if I constructed let's construct a picture over here with several subintervals. For each subinterval, I have a different midpoint. Where for the trapezoid rule, I was able to share function evaluations. So on one hand, for kind of this toy problem, I look at the midpoint rule and I say, instead of 2 function evaluations, I can just do 1, and that's really nice. But realistically, whenever we're looking at this in terms of trying to actually compute an integral using, say, a computer or something, and we're using n of 10 or n of 100 or n of 1,000, it's not an issue of, single amount of work versus double amount of work. It's an issue of an amount of work versus amount of work plus 1, right? We maybe have 1 more function evaluation to do up here than we have down here. Down here, we actually have n function evaluations. Up here, we have n plus 1 function evaluations. So realistically, even though kind of at first glance, it seems like the trapezoid rule is twice as expensive as midpoint rule, if we really dig into it, we note that we can reuse our trapezoid function evaluations from, say, the right side of a trapezoid. We can reuse that for the left side of the next trapezoid. So we're actually not really any worse off, practically speaking, trapezoid versus midpoint rule. Okay, so again, there are some other details about performance and things that that might be discussed in a course that was really devoted to these kinds of methods, but we're going to leave it there. But we can see that the midpoint rule is also exact on linears. It also has an error upper bound that's related to the second derivative. So for a linear, second derivative is 0, and the error is 0. And we see that we can make use of this nice symmetry. Okay, let's move on to Simpson's rule then. Okay, what is the idea for Simpson's rule? The idea for Simpson's rule is we want to create an integration method that is exact on, well, we did constants and linears. We want to create one that's exact on quadratics. So we saw a midpoint rule with 1 function evaluation was able to be exact on linears. Trapezoid rule with 2 function evaluations was also able to be exact on linears. We got that jump for the midpoint rule because of that nice symmetry. We expect if we want to be exact on quadratics, we're going to have to use 3 function evaluations. So let's see what that's going to look like. So here again on 0 to 1, I have a quadratic function. And I want to integrate f of x from 0 to 1, where f is quadratic. And I want that to be exactly equal to, well, here I can pick 3 places to evaluate my function. So let's say W1, or let's call it W1 f of, I'm trying to stick with my notes here, W1 f of 1 plus W2 f of 0, and then plus W3 f of 1/2. So we're going to choose to also evaluate it right in the middle here at 1/2. And the question is, can we find W1, W2, and W3 to make this exact? And based on what we had done before, it seems promising that we can do this. So if I perform this integral of the quadratic, I end up with a over 3, I get x cubed over 3, plus b over 2, plus c. And on the right-hand side, I end up with what? W1. So f of 1 is a plus b plus c. plus W2 f of 0. So ax squared plus bx plus c evaluated at 0 is just c. Plus W3 f of a half. So I have a over 4 plus b over 2 plus c. And now I see that I'm going to get 3 equations and 3 unknowns. My unknowns are W1, W2, W3, and my equations are going to come from matching up coefficients of A, coefficients of B, coefficients of C. So I see the matching up coefficients of A yields 1/3 has to be W1 plus 1/4 W3. Matching up coefficients of B, I get W1. On the left, I get 1/2 equals W1, nothing from W2, 1/2 W3. And then matching up coefficients of C, I get 1 equals W1 plus W2 plus W3. So my weights have to sum to 1. That kind of seems sensible, right? We're taking like a weighted average of our function evaluations. And so what could I do here? I could take the second equation, subtract the first. I get on the left side, so this is my B equation minus the A equation. On the left side, I get a half minus a third. Let me just move over here for this. I get a half minus a third is 1/6. W1 minus W1, they go away. Half W3 minus a fourth W3 gives me 1/4 W3. So W3 is 4/6 or 2/3. I can plug this into, let's go into the B equation. So I have 1/2 equals W1 plus 1/2 times 2/3 is 1/3. So W1 then is 1/2 minus 1/3 or 1/6. And then I note that the 3 weights have to sum to 1. So I have 2/3 plus 1/6. Well, that's 4/6 plus 1/6. And that tells me that W2 has to also be 1/6 to give me 1, to give me 6/6 or 1. Okay, so if we come back up here, W1 has to be 1/6. W2, the other kind of extreme f of 0, its weight has to be 1/6. And W3, the bit in the middle, its weight has to be 4/6 or 2/3. So if let me come down here and rewrite some of this. So I have integral 0 to 1 f of x dx, 1f is quadratic. I get this as 1/6 times, what is it, f of 0 plus 4 f of 1 plus 1 f of, f of 1/2, sorry. F of 1/2 plus 1 f of 1. So I get exact equality on quadratics if I use this weighted average of f of 0, f of 1/2, and f of 1. And again, if we imagine kind of piecing these together, we would see that this rightmost boundary is shared between, it's the rightmost boundary of this left quadratic and it's the leftmost boundary of the right quadratic. So when we piece these together, we're going to get, something like a plus f of 1 plus 4f of 3 halves plus f of 2 and so on. And this is where these 2's come from, right? If we look at our formula up here, we get the 1, 4, 2, 4, 2. These 4's are coming from these middle weights in the middle of each quadratic approximate. And the 2's are coming from the fact that we have a right boundary of a left quadratic and a left boundary of a right quadratic that are kind of matching up in the same way that that trapezoid, those boundaries were able to kind of match up nicely. And then of course, at the endpoints at the far left or at the far right, we only have one contribution because there's not a matching quadratic approximate to either side for that to match up with. Note that here, delta x was 1/2 because we did naturally have to use 2 subintervals for this problem. So that is why we have the requirement that the number of points along the x-axis that we choose has to be even. So n has to be even so that we are able to to fully construct all of these. Okay. There's one more thing that we might notice. So we expect this to be exact on quadratics. That's how we constructed it. So we'd expect that the error bound would look something like, say the third derivative, right? For a quadratic, the third derivative is going to be 0. So naturally, it seems that the error bound should be related to the third derivative. So that when the third derivative is 0 on quadratics, the error will be 0. But we actually see we get a little bit for free. The error bound is actually related to the fourth derivative. So we designed it to be exact on quadratics, but kind of for free, we get actually exact on cubics. So we get another power for free. And for these types of integration methods, these Newton-Cotes methods, we actually get this behavior. So we started with, say, the midpoint rule, which was just a certain type of Riemann sum, where we chose the function evaluation point right in the middle, and we got kind of an extra free degree of exactness, where Riemann sums are really only built, so to speak, to be exact on constants. So if I chose the left Riemann sum or the right end Riemann sum, those methods are only going to be exact on constant functions. But if I choose to evaluate at the midpoint, I get some freedom from this nice symmetry. I get some extra nice behavior, and it's actually exact on linears, despite looking like a Riemann sum. My trapezoid was exact on linears, and I kind of created it to be that way. I constructed it purposely that way, so that wasn't surprising. But then I do a little more work. I go to Simpson's rule. I add in another point. I construct it to be exact on quadratics, but again, I get that little nice jump to cubics for free. It's also exact on cubics. And again, that's due to some nice symmetry going on behind the scenes. Okay, so and then just a last little note is that you can use the trapezoid rule and the midpoint rule together with, say, n subintervals for each of those. You can take a weighted average of those to create your Simpson's method. So in practice, these kind of fourth order methods are usually the sweet spot between amount of work the computer has to do, the performance in terms of the characteristics of the error, and the complexity of the programming and of how complicated all of these weights and things are to type into the to create the program. So these fourth order methods, these things like Simpson's rule, or what it's sometimes called in differential equations, Runge-Kutta fourth order method, RK4, these tend to be kind of a sweet spot where it's not overly complex to analyze and to do the theoretical work for. It's not an enormous pain to program, and you get good trade-off between the amount of work that the computer does and the amount of error reduction you get for each marginal piece of work. Okay, so I think that's going to end the discussion today on the theoretical background behind these rules and really how they're constructed, why they're constructed this way, where all of this, where we came up with all of these formulas and these ideas.